Hey guys, in this video I'm going to go over this linear algebra problem. It says let A equal this 3 by 3 matrix. Use the Gauss-Jordan method of elementary row operations to find A inverse if it exists. For each step, clearly indicate which elementary operation is being used. So for these types of problems, whether it's a 3 by 3 matrix or whatever size the matrix is, what you want to do is you want to do a certain number of elementary row operations, so E1, E2, to whatever, to get the original A to be the identity matrix. So in this case, A is 3 by 3, so this would be the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So basically 1 on the main diagonal and zeros everywhere else. And then with these elementary row operations that you performed, you do the same thing to an identity matrix. And it would be the same size as A, so it would be 1, 0, 0, 0, 1, 0, 0, 0, 1. You do the same elementary row operations, and that would give you A inverse. So that's how you do this problem. Not all matrices have an inverse, so if it exists, you will be able to do these elementary row operations and get an identity matrix. So if you have any zeros on the last row when you reduce this matrix, then A inverse does not exist. So if this were 1, 0, 0, 0, 1, 0, 0, 0, 0, then A inverse does not exist and you can't find a solution for it. So the fastest way to solve this type of problem is to rewrite this matrix as an augmented matrix A augmented with the identity matrix. And then you perform your elementary row operations, and if A inverse exists, at the end of these elementary row operations you'll have the identity matrix on the left, and then on the right hand side you'll have A inverse. Okay, so let's go ahead and get started. So I'm going to rewrite the matrix as an augmented matrix. So 1, 0, 0, negative 2, 1, 0, 5, negative 4, 1, and then the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. The first row operation I did was R2 plus 2R1, and then I also did R3 minus 5R1. And that gives me 1, 0, 0, 1, 0, 0, 0, 1, 0, 2, 1, 0, 0, negative 4, 1, negative 5, 0, 1. And then the next operation I did was R3 plus 4R2, and that gave me the identity on the left. And on the right we had 1, 0, 0, 2, 1, 0, 3, 4, 1. So in this case, for this problem, we were able to get the identity matrix on the left-hand side. So in this case, A inverse exists, and A inverse is equal to this right-hand side of the augmented matrix. So it equals the matrix 1, 0, 0, 2, 1, 0, 3, 4, 1. And we're done with this problem.